SSRF, the Shanghai Synchrotron Radiation Facility, is a third-generation large-scale high-brilliance synchrotron radiation facility for multidisciplinary science. With its 27 beamlines and 40 end stations fully operational, as well as 8 new beamlines in development, SSRF supports the entire national scientific research and development backbone in China, and international users as well. The MX beamline, the BL17U1 biological macromolecular crystallography beamline, has been selected for this documentary in order to showcase the potential of the BDSC, the Big Data Science Center. This documentary demonstrates a real user experiment carried out in real time at the MX beamline. To avoid any degradation, the samples are kept in a nitrogen environment for the entire duration of the experiment. The users bring their samples from their home institution, and, while at the beamline, they prepare the experimental setup in order to accurately study them. The samples are moved from their original container to a temporary nitrogen box, to facilitate their handling during the setup of the experiment. From the beamline station, the samples are moved to the measurement station, where an in-depth investigation of their properties takes place using synchrotron radiation. To carry out the measurements, the MX beamline uses robotic automation. The samples are moved from the nitrogen box to the nitrogen pool, where the robot selects the samples and picks them up one by one. Then the robot, in real time, installs the samples automatically in their final position, where they are ultimately investigated using synchrotron radiation. The robotic arm exposes the samples to the highly brilliant synchrotron radiation used for the measurements, where high-resolution detectors collect, with extreme precision, all the resulting experimental patterns. Once digitalized, these patterns generate the big data deluge, which is fully analyzable in real time, only by the BDSC. The users then return to the beamline station to start preparing the experimental setup, with the alignments and adjustments necessary to optimize the final measurements. Typically, the users do not have previous experience in operating a beamline system to measure their samples. Therefore, they need extensive support from the beamline staff. Furthermore, to allow the users to properly read their results and, in the case of unsatisfactory results, to evaluate if the measurements need to be repeated with further optimization, the user training is then not only limited to the experimental setup and alignment, but also includes a full training, encompassing data visualization and basic software routines. This results in tasking the Beamline staff with extensive user training, a demanding task that distracts the scientific staff from the research and development and optimization of their beamlines. Therefore, the BDSC is additionally engaged in deploying machine learning, artificial intelligence, or AI, and facility-wide automation in order to dramatically reduce the staffed user support, thus allowing the scientific staff to dedicate more time to the upgrade of their beamlines, using the most advanced and up-to-date science and technology. The alignment and setup process can thus commence. Throughout the entire experiment, a nitrogen environment completely protects the samples from degradation, guaranteeing pristine and high-quality measurements. A sample holder hosts several samples, which are equally mapped into the beamline measurement system. From there, the robot picks up the samples that are selected by the users for their measurements. The Beamline staff introduce the users to the sample alignment procedure, which will result in the optimal final configuration necessary to produce high-quality scientific results using high-brilliance synchrotron radiation. Here, the users learn how to inspect their samples visually before the actual synchrotron measurement takes place, which produces high-resolution diffraction patterns. These experimental raw patterns, after being processed, produce the final 3D user sample reconstructions at atomic resolution. The users are thus introduced to reconstructing their raw data and inspecting the quality of their samples and measurements, while transparently using the advanced BDSC analysis capabilities, including massive parallelization of their data pipelines. Each pipeline reports on the quality of the final results, and all the scores are stored as metadata into the BDSC Big Data Framework, together with the corresponding experimental data, which are then ingested by neural networks using machine learning to train the BDSC scientific AI. The resulting AI will then be responsible for fully controlling the automated experiments at the beamlines through extensive robotic automation. This, ultimately, will make possible autonomous AI-assisted experiments at the large-scale scientific facilities, encompassing raw big data production, visual inspection of the preliminary results, and the final 3D atomic and molecular reconstructions. After the training, the users can now progress, unsupervised, with their experiment. Further monitoring all their data jobs, which are transparently sent to the BDSC for the analysis of their samples. Using the Beamline control software, the users select the samples for their measurements. Then, in real time, the robot executes the measurements promptly matching the user requests. The operations are monitored from the Beamline station by the users and staff, where the samples can be visualized and their measurement conditions optimized before the actual synchrotron measurement takes place. After a successful visual inspection, all the parameters for the measurement are set and the synchrotron measurement takes place, resulting in a diffraction pattern collected by the detector inside the measurement hatch, right in front of the sample while it is being irradiated with synchrotron radiation. The users may thus visually inspect these raw patterns. Meanwhile, all the corresponding raw big data are sent to the BDSC for further analysis. BDSC, the Big Data Science Center, which resulted from the SSRF Phase 2 upgrade project, is in charge of the entire scientific computational framework of the SSRF, augmenting SSRF with state-of-the-art big data, AI, and robotic automation science and technology, effectively creating the first superfacility in China, and one of the first worldwide. At the BDSC, hybrid CPU-GPU superclusters, supported by the latest generation of highly resilient and efficient storage systems, optimized for high throughput and high workload, and by an InfiniBand network backbone, equipped with low latency switches, relentlessly analyze the enormous flow of uninterrupted big data, originating from all over the SSRF. Here the BDSC IT staff work, supporting the BDSC operations. The BDSC control room is the vital core, encompassing the entire BDSC infrastructure. From here, the BDSC research and development staff tirelessly manage, supervise and control the entire BDSC framework, ensuring that all the big data originating from SSRF are analyzed, interpreted and visualized in real time with state-of-the-art big data and AI science and technologies. Here is where the BDSC superfacility platform is deployed, equipped with a high-performance computing, or HPC, scientific cloud and an advanced workload balancing system, capable, if necessary, of elastically scaling out the big data produced at SSRF to the national supercomputers in China.
the Big Data Science Center, the BDSC, has designed, architected, developed and deployed a novel big data science platform at SSRF, the Shanghai Synchrotron Radiation Facility, which allows all the users at SSRF to fully exploit the scientific and technological potential of the BDSC for their own research. The BDSC is now fully operational, and we are constantly upgrading its infrastructure. Here, in fact, the state-of-the-art big data science and technologies, artificial intelligence, Internet of Things, real-time remote unmanned experiments, robotic automation, HPC, cloud and fog supercomputing, and massive parallelization are converging at the SSRF through the BDSC fully centralized platform. This resulted in an acceleration of the user multidisciplinary science carried out at SSRF of an outstanding factor 60, and effectively creating the first ever world-class, user-friendly super facility here in China. This is greatly augmenting the interpretation of all the scientific data generated by all the experiments at SSRF. The BDSC, with its big data science platform, is thus fostering full robotic automation throughout the SSRF beamlines, aiming at real-time unmanned experiments while sharing its successful experience with all the other multidisciplinary large facilities worldwide.
Leveraging advanced HPC containerization technologies, optimized for efficiency and low latency on big data workloads, the BDSC Big Data Framework maps all the data produced at SSRF, transforming them into machine-readable data flows, ingestible by neural networks, through machine learning, for AI training, and targeting autonomous robotic experiments at SSRF. The BDSC further leveraged big data visualization capabilities, returning, as much as possible in real time, final results to the users, ready for them to be studied and published. This is instead of a plethora of raw big data, which would force the users to spend months to just get them analyzed. The BDSC thus aims to dramatically accelerate and automate multidisciplinary user research, covering the widest range of scientific disciplines from medicine and pharmaceutical science to energy and materials science, physics, chemistry, bioscience, nanotechnologies, electronics, manufacturing, environmental science, archaeology, and many more. This effectively increases the rate at which the users produce scientific discoveries and resulting technological advancements, with a clear societal impact. While still at the Beamline, the users can now directly review their final results obtained from the BDSC Big Data Framework, and, if necessary, use these results to further optimize their experimental configuration, and then repeat their experiment using result-informed optimal parameters. Therefore, the users will no longer return home only to discover, after months of data analysis, that they have collected bad data. Instead, through the BDSC Big Data Framework, they will be able to dramatically maximize the amount of high-quality data they can collect during each beam time, and which can be thus readily included in their publications, therefore, in turn maximizing the SSRF users' satisfaction. Thanks to the BDSC framework, the users can now, also remotely, easily access all their data resulting from their experiments at the SSRF, through thin terminals, using one single user-friendly interface. From here, the users can navigate through all their scientific results, which are connected with their raw experimental data, and enriched with metadata. Through the BDSC superfacility platform, the users can remotely transfer all their data stored at the SSRF. At the same time, SSRF can make use of this system to manage users' proposals and their beam times, while keeping up to date the list of publications of all its users, as well as managing all its policies facility-wide, thus effectively using the centralized BDSC superfacility platform to unify the entire large facility lifecycle. Furthermore, from here, the users can access all the information regarding their datasets and connect them with their publications. Meanwhile, using the BDSC infrastructure for further analysis. Moreover, here the users can gather all the details of their samples, while connecting them to their experiments, proposals and datasets, all in one place, within the unified BDSC interface. All this information will further enrich the metadata pool, used to create and train the next generation AI for science, shifting the focus of all the SSRF users, from data science to pure science, and thus enabling the creation of a true user science-centric and multimodal infrastructure. Here, the massive support offered by the BDSC in terms of scientific computation is required in order to enable the most complete knowledge transfer, from scientific research to industrial developments. In fact, the BDSC is firmly focused on maximizing the satisfaction of both users and facility staff.
大家好，上海光源是中国大陆第一台第3代同步辐射光源，建成于2009年。2016年，上海光源启动了最大的后续现代工程建设——上海光源2期现代工程，预计本年底全部建成。2期现站大大扩展了实验能力，使得上海光源的时间、空间、能量、动量等分辨能力近乎达到了第3代同步辐射光源的极限。同时，配套建设的离线用户辅助实验室，大大增强上海光源一站式服务能力。建设的用户数据中心将使用户享受到高效的数据存储、计算以及在线实验知识，加速上海光源的科学产出。截至目前，上海光源已经有27条光束线，近40个实验站投入运行，接待学界、产业界等的用户总人数超过了3.5万人，产生了一大批有重要影响力的重大用户成果。欢迎大家来使用上海光源，谢谢。